Ever had a plastic toy snap unexpectedly in your hands, leaving you puzzled and perhaps a bit frustrated? Or maybe you've experienced a container lid cracking for no apparent reason, right when you needed it most. It feels random, like a stroke of bad luck, but it's not just chance. Most plastic failures are actually preventable. Tiny design mistakes, often overlooked, set them up to break long before you ever use them. These flaws are like hidden traps waiting to spring. This isn't just about toys or kitchenware. Consider your laptop case, car parts, or even critical medical devices. When plastic fails in these areas, it's a big deal, potentially leading to costly repairs or even safety hazards. The real culprit? Classic design errors that engineers make all the time, often due to oversight or lack of understanding of material behavior. Today, we'll reveal the most common mistakes that turn plastic parts into ticking time bombs, ready to fail when you least expect it. Whether you're an engineer, a 3D printing enthusiast, or just someone tired of dealing with broken stuff, understanding why plastics fail is like having a superpower. We'll show you how plastics behave differently from metals, what makes them snap under pressure, and how to spot design flaws before they cause chaos in your life. By the end of this journey, you'll see every piece of plastic around you in a new light, understanding its strengths and vulnerabilities. Ready to become a plastic part detective? Let's dive in and uncover the secrets of plastic failures. Together, let's turn those frustrating cracks into design wins, transforming weaknesses into strengths. The first rule of working with materials: plastic is not just a cheaper version of metal. It's a completely different beast, with its own strengths and weaknesses. If you treat plastic like it's just a lightweight metal, you're setting yourself up for failure. That's a recipe for disaster. And it's a mistake many engineers make early on. Metals are strong in all directions, predictable, reliable, and consistent. You can usually count on them to behave the same way, no matter how you load them. Plastics, on the other hand, are more like spaghetti. Strong along the direction they were molded, but much weaker across it. Their internal structure is complex, and that makes them behave differently depending on how they're shaped and loaded. Ignore these differences, and your plastic part could fail under loads it should easily handle, sometimes suddenly and without warning. Then there's creep. Metals will stretch a bit and then stop, but plastics keep stretching under a constant load, sometimes for months or even years. This slow deformation can lead to unexpected failures long after the part is put into service. Temperature is another critical factor. Plastics can become brittle and crack in the cold, or soften and deform in the heat. Their properties change dramatically with temperature swings. Take a car dashboard, for example. It has to survive freezing winter nights and scorching summer days, all while looking and performing the same. And don't forget about impact. Plastics can handle a slow, steady pull, but a sudden impact, a sharp hit, can shatter them instantly. They're far less forgiving than metals when it comes to shock loads. The takeaway? Plastics are sensitive to the direction of force, to temperature, and to how you load them. Every detail matters. Good design means understanding these quirks and working with them, not against them. It's about anticipating how your part will behave in the real world. Don't just copy metal designs. Think like a plastic engineer. Adapt your approach and design specifically for the material you're using. Know your material, know your environment, and test your designs under real-world conditions. That's how you avoid early failure and create plastic parts that last. Plastic parts fail in a few classic ways, each with its own story. First, brittle fracture, the sudden crack, often from stress concentrated in one spot. Next, warping, parts twist or bend out of shape, usually from uneven cooling. Then, fatigue. Tiny cracks grow with repeated use, like a clip that snaps after months of flexing. And finally, creep. Slow, sagging under constant load, like a shelf that bows over time. Each failure type points to a different design flaw. Your job? Know which failure you're fighting and design to prevent it. Don't just hope for the best, plan for the worst. Spotting these failure modes is the first step to making parts that last. Every crack, warp, or sag is a clue. Learn to read them, and you'll design parts that survive. When plastic breaks, we blame the material. But over 90% of failures are really design mistakes. The plastic just followed the laws of physics. The design set it up to fail. Great design can make cheap plastic perform like a champ. Bad design can ruin even the best material. Most flaws sneak in when engineers think like metal workers, not plastic specialists. Sharp corners, thick walls, and cool features often create hidden stress and warping. The real question isn't what's the strongest plastic, but what's the smartest design? Master the basics, and you'll prevent most failures before they start. The number one plastic design sin: sharp internal corners. A sharp corner is a stress magnet. Cracks almost always start there. Stress flows like water. Sharp corners create turbulence and high pressure. That's why cracks often begin at these points, leading to sudden failure. The fix is simple. Add a fillet, a rounded edge, at every internal corner. A fillet spreads out stress, making the part much stronger. Rule of thumb: fillet radius should be at least half the wall thickness. Even a small fillet is better than a sharp angle. Look at any quality product. You'll see rounded corners everywhere. It's not just for looks, it's essential for durability. Next time you see a cracked part, check the corner. It's probably sharp. Round those edges, and you'll stop cracks before they start. Inconsistent wall thickness is a classic plastic design blunder. When thick and thin sections are side by side, they cool and shrink at different rates. This creates internal stress, warping, and ugly sink marks. The solution? Keep wall thickness as uniform as possible. Need more strength? Use ribs and gussets, not thick blocks. If you must change thickness, do it gradually with smooth tapers. For example, a box with uniform 2mm walls will mold perfectly. Make the base 5mm thick and the walls 2mm. Expect warping and bowing. Instead, keep the base thin and add a grid of ribs for strength. Uniform walls mean stable, good-looking parts. Plan your thickness and your parts will thank you. Ribs add strength without bulk, but only if designed right. Too thick, and they cause sink marks and warping. Keep rib thickness to 50 to 60% of the wall. Snap fits and living hinges are brilliant, but only with the right material and geometry. Use flexible plastics like polypropylene for hinges. Brittle plastics will snap. For snap fits, always add a generous fillet at the base to avoid stress points. Living hinges need the polymer chains aligned across the hinge. Think about mold flow. Simulate critical features with FEA before cutting steel molds. Follow the rules: thin ribs, flexible materials, and fillets everywhere. Get these right, and your dynamic features will last. Ignore them, and you'll have a pile of broken parts. Let's dive into some real-world mistakes and see what we can learn from them in action. Sometimes, the best lessons come from things that go wrong, not right. Take this handheld scanner, for example. It kept falling apart during use. Its snap-fit hooks broke off again and again, frustrating both users and engineers. The main culprit: sharp corners at the base of those hooks. These sharp edges created stress points, making the plastic weak and prone to cracking under pressure. The fix was simple but effective. Add a smooth fillet to those corners and switch to a tougher, more resilient plastic. Suddenly, the hooks stopped breaking. Problem solved, and the scanner became reliable. In another case, a plastic chair had a thick seat and thin legs. At first glance, it looked sturdy, but the design hid a big problem. The result? Sink marks and warping. The thick seat cooled much slower than the thin legs, pulling the chair out of shape and leaving ugly marks. The solution was to core out the seat, making the thickness uniform, and then add a rib grid underneath for strength. This redesign balanced cooling and boosted durability. The new chair design was lighter, stronger, and molded perfectly every time. It looked better and lasted longer, all thanks to a few smart changes. These real-world fails show how even small design tweaks can make a huge difference in performance and reliability. Most disasters in plastic parts start with a sharp corner or a thick section. Tiny details that can lead to big failures if ignored. Spot these issues early in the design process, and you'll save time, money, and a lot of headaches down the road. Learn from these mistakes, and you'll design like a pro, avoiding common pitfalls and creating better products. Remember, every failure is a valuable lesson. Use it to improve, innovate, and become a better designer with every project. Here's your ultimate checklist for plastic parts that last. Choose the right material for the job. Don't just go cheap. Keep wall thickness uniform and blend transitions smoothly. Add fillets to every internal corner. No sharp edges allowed. Make ribs thin and well spaced. Avoid thick sections. Account for shrinkage and always check the material data sheet. Simulate and prototype critical features before production. Remember, great design, not just great material, is what makes plastic parts survive.